Hello students, welcome back. Now we are going to start our discussions on a new sequential circuit, and those are called registers. So in this video we are going to talk about that what is a register, the basic functionality of a register, how can we design a register using flip-flops, and how do we implement them using Verilog. So let us get started. So first of all, we should know that what is a register. A register is designed to store the data values. It can store more than one bit, and that is the main difference between a register and flip-flop. A flip-flop can store only one bit, whereas the register can be designed in such a way that it can store more than one bit. The register will store the data, it will hold it until we load a new data value. They are designed to load and hold. This is the basic functionality of a register. Now, when we talk about the register design, one of the first register that we design is a 4-bit register. That means it is going to have 4 pins for the input and 4 pins for the output. A clock signal will be used which will control all the bits at one time. So whenever we are going to receive the rising edge of the clock, the data on every bit will be updated. Either all of them will be retained to the same value or a new value will be updated in all the bits. So register will hold the data, and until the clock is there, it will retain it and wait for the next rising or the falling edge. So now, how can we design it using Verilog? Well, the logic is simple as we understand, and the code is also simple. We will simply say at the rate positive edge of the clock, output is equal to input. So that is the simple code. A one-line code can define your 4-bit, 8-bit or any bit register. Now let us look at one more alternative. Here I have an arrangement of one multiplexer and one flip-flop, and we are saying that this is a 1-bit register. So how does this work? So here we are having a load signal which is used to decide the operation. Load signal is the select line for a 2x1 multiplexer. If load is 0, it is going to select 0, and you can see that 0 is connected to the output of D flip-flop. That means the same Q will pass down back to the D. Next time, if I keep load equal to 1, then whatever is the value of D, that will be transferred to the input of flip-flop. So now you can see that we are having both the functionalities. If load is 0, we are retaining the last output, and if load is 1, we are loading the new input. So now what we can do, we can extend the same logic to more number of bits. Now let us design a 4-bit register by extending the same logic. So here we have the circuit diagram, and you can see that what we have done here is just take 4 replicas of the same circuit. The clock of each flip-flop is attached to one single signal. Similarly, the load signal, which is the select line for 4 different flip-flops, is also same. That means all the 4 bits are going to perform the same operation at same time. Now we are going to implement a register using both the techniques in Verilog. We start with the design source creation, and first thing that can be a mistake, that you can give the name as 4-bit register. This is very intuitive, but it is going to give you the error because the first character should not be a number. So you can give register underscore 4-bit or anything like that. That will work. Then we finish. So what do we need? We need one input. You can call it in or D. And then I say it is a bus from 3 down to 0. That means total 4 bits. We are having a clock and we are having the output Q. Again, we will click on the bus and 3 down to 0. So this is all. Then we say OK. And here we have our register. We are going to say first that there is a register which is 3 down to 0 and the name is Q. Okay. Always at the rate you can define negative edge or positive edge of the clock, begin and end, and what we have to do, we have to simply say that Q is equal to D. So this is a simple register which will always keep on looking that what is the value of D and allocate it to Q at every negative edge. We save it and let us check the simulation directly. The simulation environment is ready. I am setting my clock as 100 nanosecond clock and we are setting data input as a constant. This is hexadecimal number, so you can give any hexadecimal number in 4-bit. So I am writing 8 and I run for slightly more than the 100 nanosecond clock, so 120 nanosecond. Now you can see this is 8, this is 8. Now I change the value here and I say let it be B and I run it again. This time I am not changing the value, I just run it. Okay. Now I change the value again and set it to 3 and run it one more time. And one more thing we can do is change one more value and run the simulation. And let us now check that what is happening at every time. So we zoom and what we find here is quite interesting. First of all, I set it 8 and whenever the negative edge is coming, exactly here there was a negative edge, so it was allocated 8. This is my next negative edge. Whatever is the value, the same will remain. Look here, the value of D is changing, but the value of Q is not changing because there is no negative edge. So when the next negative edge will come, then the value B will be allocated. We can observe that all the subsequent changes in the value of output are at the negative edge of the clock. We can observe that after this B is changing to 3 and then 3 is changing to 7. Both these changes are also at the negative edges. Now one thing that you can do is right click and say radix as decimal. So B is basically 11. So you can read your numbers in any radix as well, in binary format, in hexadecimal, in octal, in decimal, anything. Now let us code the 4-bit register using a combination of 4 multiplexers and 4 flip-flops. So first of all, I have this D flip-flop where there are 3 ports. 2 of them are inputs, D and clock, and one is output, which is Q. Then I have this multiplexer where there are 2 inputs, I0 and I1. Then there is select line and one output Y. This is the order I have to remember. So I come back to my code and I use the multiplexer first. mux underscore 2x1 underscore gate. Then I give certain instantiation like M0. So I0, I1, select line and Y. This is the order. So what is I0? That means Q of 0. The same data. What is I1? That is D of 0. Then what is the select line? That is our load signal. And what is the output? The output will go to the input of D flip-flop. That means I need to have some wires. So I will declare wire. You can also declare wire as a bus. Okay, 3 down to 0, and you can call it S. And here we say S of 0. And we close this instantiation. So this is my first multiplexer. I can copy this and carefully edit all of them. So this is M1, M2, M3. Q0, 1, 2, 3. D0, 1, 2, 3. Load will be same for everyone and wires will change. Now coming to the D flip-flop connection. So DFF, DF0, and then first of all we need to give that what is the input. The input is the wire, that is S of 0. Then we need to mention the clock. So we have the clock, and then the output. So that is Q of 0. So this is my first D flip-flop. I will copy it 4 times and then again change the instantiation. This is one mistake which we normally do. We don't change the name here. 3, 2, 1, 0 and 1, 2, 3. So this is our code. We don't need to mention anything else. We save it. There is one thing that we should make sure, that we should not define Q as register this time, because Q is going in the output as well as input. So the good thing will be to define Q as a wire. So this is one correction and one thing that you should take into your mind whenever your variable is going into the output as well as input ports. Now we are going to check the schematic for the same. So we can check the schematic that there are 4 flip-flops. All of them are having one select line, that is load signal. There are 4 flip-flops. All of them are being controlled by one clock, and we are having our 4-bit output. So I have run the simulation. What I have done here, I took clock as a 100 nanosecond clock, and load value I am changing. I keep it 0 for maximum time and I keep it 1 also for some time, and then I am giving different values at D. Now at every positive edge of the clock we will see what is the value of load. If load is 0, we will hold. So here D was not defined, so it is holding the undefined values only until we load a proper value. So till this point, at this rising edge, it was not defined, so we are not loading anything. Now here we are loading something and the value is 3. So now 3 is loaded into Q. Now what we do, we check at every rising edge. Here load is 1, so we will load 3. Here load is 0, so we will hold it. So we keep on holding, and at this rising edge we find that the new value is 4 and we will load 4. Until that we keep 3. So this register is also working in the exactly same manner. So students, now we have designed a simple register. Let us design a register with some more functionalities in our next video. Keep learning. Thank you.